Good day. Today I will speak about arbitrary layered model inversion for electrical resistivity data. For ERT data, it can be problem because it's very often when resistivity in near surface part changing very strongly. So it's necessary to do something with top layer to make this kind of model work. So let's start with one project. It has high resistivity top part, near surface high resistivity, and some place has low resistivity. So it's quite heterogeneous, and it should be prepared, data should be prepared for the arbitrary layered inversion. Now let's see what kind of options we have in software to do it. First of all, we have special option which allow first cell layers to have more freedom to. So a resistivity, big resistivity changings are allowed in this first layer. So I'll choose one first layer, and I think it's enough. Next option, I'll try to improve layered part of model. So inversion will try to make my model more layered, improve this part of structure. It can be made here. So let's use some correlation function to minimize between cells in horizontal direction. And also I'll use one layer off. It's not be correlated, so it's give it a little freedom. And now I just will do an inversion of this data set for mesh model. It can take a little longer. And while inversion doing, I will speak about arbitrary layered model again. Arbitrary layered model is not 1D model. It has the same full 2.5D solution, but it has some limitation inside the layer. So resistivity inside layer change linear, like linear function between resistivity nodes. So it can this model can approximate situation when geology is layered or pseudo layered, and we can in this case do this kind of inversion. But data, as I said, should be prepared because here you can see after for iteration, there is many heterogeneous cells. So it's big changes in resistivity of first layers. For processing this situation, I think it's enough for inversion. We use theory of equivalent dipoles. So we can process our data to avoid this P and C effect, which electrodes lie near some resistivity contrast with our model. So we just need now to smooth our top layer have special option for it. Let's remove cutting. So I'll select first layer and I'll try to smooth this selection twice. And after I will make another smoothing for first two layers. Also twice. It gives us a pretty smooth top layer, and it's a big chance that all this resistivity contrast in top layer, we just modeled our static shift effect P and C in data. So it's not distorted our data a lot, and this operation can be applied. So it's not so much distorted data, so the await result will be very similar, but without this heterogeneities in the top layer. So now I'll recalculate forward problem. It looks very same, but there is no these details which can be produced by first layer. And now we can copy our calculated data to measure it. And go to layered model mode. So I think we need to switch to this kind of image. And to see together layered model and mesh model, I just make my layers transparent. It's definitely 4 layers model, so I need to add one more. Here I can change some parameters. Maybe to make my borders more close to this resistivity anomalies. And I'll do my border more detailed. Now I have layered model, first approximation of it, like horizontal layered model, and my boundaries close to resistivity boundaries in mesh model, and I can took resistivity for nodes, resistivity nodes from mesh. Now I have some averaged resistivity in every nodes of every layer. As I said, this is resistivity nodes, and resistivity will change between these two nodes in layer as linear function. So now we can just do inversion already for arbitrary layered model. Let's remove transparency. Start. There is a lot of parameters for inversion, but we can change it for first, for top layer and all other layers. And this method always need optimization, should be turned on, because It's very important for this kind of inversion. It's strongly non-linear. And if we have which kind of anomalies, this is very important to have resistivity nodes in the same place, because here, as you can see, it's changed along layer, along distance. But anyway, I would stop inversion. We got pretty good misfit for this layered model. And now we can use it. I will turn on cutting again. And what we have as a result of this inversion, it's whole layered model. Now we can copy back our layered model to mesh model and try to make inversion again. I just remove this layered theorem from optimization. And after we can compare two models. I think 2 iterations will be enough. It's already very small misfit. So we have this model. Let's change color scale and make layered model transparent. So it's very close. Thank you for your attention and see you again. Bye.